All right, let's get started here. Good morning, everybody. Welcome to 16B co-class. You guys have been sending me some questions, which is great. I have a few things I will just start with in a moment here. If you have questions you want to ask, feel free to ask me via your voice or to send it in the chat. Also, wanted to point out a couple things just in general. Oh God, what was Sarah telling me? Sorry, I had a couple things and now I've forgotten them. If you see me making an error, feel free to speak up right away. Also, if you ever want to say something but you don't feel like you want to say it in front of everybody, it's perfectly fine. You can always send me a private chat and hopefully I will see that if I'm looking at my computer. So just a couple things. If you see mistakes, let me know. I do on occasion make errors, so definitely using log rules. Indefinite intervals using log rules. I think so. I guess I'm not sure what you mean exactly, but I will. If you send me, write me an example, and I will see what, and I'll try and see what you mean. I'm going to do a couple other examples first. But Fernanda, if you want to kind of write me something, I will do an example like that. Sure.
Can we also do in FAM's like web assign homework? It's something that asks like, what does u and du over dx mean?
Sorry, say that one more time.
It's like, what does like identify u and du over dx, and what does it mean? And then could we do like an example of that? I wrote one down if I can get in it. Thank you.
Okay. All right. So I've got a couple examples, but I definitely see, so integers is exponentials, certainly. Solving that with integrals. I'm still not exactly sure what you guys mean. So let me just clarify the integral thing real quickly. I don't imagine you guys are asking about finding the antiderivative of natural log. Because, back to Fernanda's question. Using log rules, I don't think that's what you're asking about, so I guess I'm not really sure about that. Yeah, okay, I think we're good to go. If you have questions, go ahead and feel free to put them in the chat. I might not see them right away because I'm going to be standing at my board, but you guys know the drill. I can pop out the chat. Oh, that's super smart. Haha, yeah, I'm brilliant. Not really. Good, but now I can see the chat separately. Awesome. Okay, oh sure, yeah. Oh yeah, so yes, I saw your email as well, Denise. So let me do a couple things first. So people, you guys did a great job on the quiz because I accidentally asked a question that I didn't mean to ask, which is fine. So first of all, I did post solution to the quiz on Canvas. So if you want to look at that, you're welcome to. But just to remind you, I asked this question. I asked the derivative of the integral from 2 to x of t to the 7th. And I don't remember if it was plus or minus. Let me take a look real quick here. Sorry. Oh man, come on, files. Sorry, my computer's being dumb. 1 minute. Apologies. New. Also, my hair is going to get real long as this goes on, and it's already getting pretty crazy. So you guys are going to see some fun hair eventually, I'm sure. Let's see. Quizzes, quiz 2, I forget. Just remember what I asked. Take your time, take your time. All right, it was a minus, okay. So this was the question I asked. And so here's the thing I want you to really know about this. You can totally do this the long way, and we will do it the long way. But the way you really should be doing this sort of question in general is saying, oh, I know that the derivative of the integral from something that's constant to x of whatever this function is always just going to equal, that's f of t, is always going to equal whatever that function is, just with t replaced by this x here. So you can always answer a question like this, the derivative of the integral from a constant to x of some function of t is always going to equal the function of x. Now, I also said you could do more work if you wanted to, which is fine. And there is a long way to do this. Now, I kind of made a mistake. I meant for this to be cosecant squared because the antiderivative of cosecant squared is really easy. It's just negative cotangent. Right? I know the derivative of cotangent is negative cosecant squared. So the antiderivative of negative cosecant squared is positive cotangent. But I made an error. I accidentally put cotangent squared there. Whose antiderivative is not so easy. A lot of you figured it out, which is great. So to do the antiderivative of cotangent squared, so I'm actually going to write this out. So what people ended up doing, I'm going to write the derivative here in a minute, but I'm just going to do this part first. People recognized that there's a trig identity for cotangent squared. The trig identity is, I think this pen is trash. Sorry, I'm over here. So the trig identity for cotangent squared is 1 plus cotangent squared x, or t, or whatever your variable is, equals cosecant squared x. So people then took that, solved for cotangent. So cotangent is equal to cosecant squared minus 1, and replaced cotangent squared with cosecant squared of t minus 1, which was smart. And then they distributed the minus sign, which I'm just going to do real kind of lazily here. I'm going to erase the parentheses and distribute the minus sign to here and to there, which makes that a plus. And then people did the antiderivative. So they got antiderivative t to the 7th is t to the 8th over 8. The antiderivative of negative cosecant squared is positive cotangent, right, because the derivative of positive cotangent is negative cosecant squared. I'm really going to keep emphasizing this relationship. If you take the derivative of something, you can take the antiderivative of that result and get back to the original thing. So the antiderivative of this is that, the derivative of this is that. And then the antiderivative of 1 is just t. Whenever you antidifferentiate a constant, you just get that constant times the variable. So if you were antidifferentiating 7, you would get 7 times t, or 7 times x, depending on what variable you're using. I don't use a plus c, because this is a definite integral. We never need the plus c. You can write it, but we'll end up canceling out. So, and then I'm going to plug in the x and plug in the 2. So I'm going to get x to the 8th over 8 plus cotangent of x plus x minus, and plug in the 2, I get 2 to the 8th over 8 plus cotangent of 2 plus 2. Finally, so that would be all the antidifferentiation, but then we're going to differentiate all of that. So we're really taking the derivative of all of this. I think I can put it in here. So here's the thing. The derivative of x to the 8th over 8 is just 8x to the 7th over 8, and the 8's will cancel. The derivative of cotangent of x is negative cosecant squared of x. The derivative of x is 1. The derivative of 2 to the 8th over 8 is 0 because it's a constant. The derivative of cotangent of 2 is 0 because it's a constant. The derivative of 2 is 0. This second part, the derivative is always going to end up being 0 if you're plugging in a constant here. Finally, we can simplify this and see that we get x to the 7th minus cosecant squared plus 1. But minus cosecant squared plus 1 is really just minus cotangent squared. So this becomes, sorry, I know I've run out of room here, x to the 7th minus cotangent squared of x, which is the same as if we just did it the short way. So again, that's part of the fundamental theorem of calculus that just says the derivative of the antiderivative of this function is just the same function, but with the variable x instead of the variable t. So yeah, this problem, I said you can either do it the short way and just be like, there's my answer, or you could do it the long way and kind of see, oh yeah, if we antidifferentiate and then differentiate, we do end up back at exactly the function we started with, just with the variable x to the variable t. Yeah, so problem 2, I don't remember exactly, let me see, I know I pulled it up. Problem 2, you just have to find the antiderivative. Problem 2 was problem 2 was a definite interval, I think, where you had to plug in ones in the sheet. Yeah. Let's look back at this chat and see what you guys got here. Sorry. Once again, here is the attendance form. Please go fill it out once and only once. I will check later to see. Even if you're not enrolled in the class in Canvas, still fill out the attendance form. Everyone should fill it out. So let's go back and look at the. Oh yeah, sorry. There was another. So before we get to all the questions in the chat, which we'll definitely get to, there was one other question. Actually, 2 other questions people had from Merck's homework that I just want to address real quickly. They have to do with kind of exponential growth and decay. I know that's kind of in the past, but I still want to get them really quickly. So there was one about charcoal and radioactive decay. So basically, I'm going to make up slightly different numbers. They said that charcoal, a piece of charcoal has, I'm going to say, 23% of the radioactive carbon, as it would, and half-life is, what's it, 5,715 years. How old is it? So whenever you're dealing with exponential growth or decay, you're using this kind of setup. Y equals to C e to the ket. And here's the thing, we don't actually know how much we're starting with, right? They just said we have 23% of how much we started with. So if I'm being given things in terms of percentages, I usually like to just pretend I'm going to start with 100%, or 100 grams, or just 100 units, so that then the percentages work out really easily. So I'm going to say my C value, my initial value is 100 units. So then my model is looking like y equal to 100 e to the ket. And here's what I know. I like to make this a little chart usually. I know that time equals 0. I'm starting off with 100. I know that time equal to 5,715 years. I have half, right? That's what it means to be the half-life. Is that much time later, that's how much you have. So I have half of what I started with. And then I'm trying to figure out what time it will be when I have 23%. Well, 23% of 100 is just 23. So I'm going to use this information here to figure out what the K constant is. So I'm going to plug in Y. And the reason I also like to make this chart is so I don't accidentally plug in the wrong thing for Y and for T. So I was like, oh, Y is 50 and T is 5,715. So I've got 50 equal to 100 e to the K times 5,715. And then we can solve for the K value. Divide by 100. 50 divided by 100 is 1/2. That will always happen when you're using the half-life. That's going to equal e to the K times 5,715. Take the natural log of both sides. Natural log of 1/2 equals the natural log of e to the stuff is just the stuff. Finally, K is equal to natural log of 1/2 divided by 5,715. This is generally true, by the way, if you're ever finding the K value for radioactive decay, the K value is always equal to natural log of 1/2 divided by the half-life time. That's always true. You've maybe seen this in chemistry. Sometimes people say it's negative natural log of 2 divided by that, which is the same thing. So something to be aware of. Now, if I'm going to find out how long it takes until there's only 23% left, well, I'm going to erase a little bit. I'm going to take my model, which now I've solved for K and for C. My model is now given by y equal to C e to the K, which is natural log of 1/2 over 5,715 T. And then we can figure out what time it is when there's 23% left by setting T equal to 23. Sorry, not TT. I was about to make a mistake. I'm not setting T equal to 23. I'm setting Y equal to 23. So I'm going to say 23 equals all that. I'm going to be a little bit lazy here. And you just plug in 23 right there. And then we're going to solve for t. And so then that's pretty much the same process that we just used for solving for k. I'm going to divide both sides by 100. So 23 divided by 100 equals all of that, e to the all of that times t. Kind of gross. We take the natural log of both sides to get, to get this down into the exponents. It's the natural log of, you could say this is 23 over 100, or you could say it's 0.23 equals all of that. Natural log of 1/2 divided by 5,715 is t. And then to solve for t, I'm going to multiply by 5,715 and divide by the natural log of 1/2. And I would leave my answer like that unless they asked me to give a decimal approximation. If you were doing a decimal approximation, where'd my good calculator go? I've got one garbage calculator and one good calculator. So if I was going to calculate this, let's see. I'm going to have natural log of 0.23 times 5,715, which is negative, and then I divide by natural log of 1/2, which is also negative. And I end up with about 12,117 years. Now, for the actual number you have, it should probably be longer than that because it's going to take longer to decay further to 13%. But that's kind of how you look at a question like that. All right, one more exponential growth decay type problem, and then we'll move on to all the fun anti-derivative stuff that I know everybody wants to talk about. And this is actually similar. This is actually the same question that I think Craig asked in one of the discussions. I don't think anybody provided an answer to it. I think he was actually, I know that his mistake when he was working on it was he was accidentally interchanging the n and the t values. So that's, again, why I think it's really good to make this little list. Where did the question go? So the question goes something like this. We have kind of this model. The number of units produced per day is modeled by 30 times 1 minus e to the ket. Where, and just as something to point out, as t gets larger and larger, this is going to get smaller. This is going to get closer to 1 because our k value is negative. So here's what we know. We know that when t equals, and I'm going to make up different numbers because I'm going to say, so let's say when t equals 17, so on the 17th day, the worker is producing n equal to, let's say, let's make it interesting. Let's say 12 units per day. And then I want to know how many days until they're producing, let's make it 18 units per day. And again, I think this is a really excellent time to use that table I was using because, well, as someone pointed out to me, it's really easy to accidentally interchange t and n of t. So I know when t is 17, n of t is 12, and I'm asking how many days, so what time is it when n of t is 18? So I'm going to plug in 17 for t and 12 for n, solve for k, and then plug in 18 for n and solve for t. So doing it this way, let's see. So n of t is 12. And that's equal to 30 times 1 minus e to the k times t, which is 17. Divide by 30. Yeah, either way. 1 minus e to the 17k. I'm going to bring the e thing over here and the 12 over 30 thing over there. So e to the 17k equals 1 minus 12 over 30 reduces to 2 over 5. Taking the natural log of both sides, 17k equals the natural log of 1 minus 2/5 is 3/5. So k is equal to the natural log of 3/5 divided by 17. Then we're going to jam that back into our equation and plug in 18 for n. So now my equation looks like n equal to 30 times 1 minus e to the, this kind of gross number for k, natural log of 3/5 divided by 17 times t. That's my model for the production per day at time t. And then I'm going to plug in 18 for n of t. So 18 goes right here. That's all of that. And again, the way you solve this, so last time I solved it by dividing by 30. If you really wanted to, you could actually distribute the 30 first. So you could say 18 equals 30 minus 30 times e to the all that stuff. And I know it's kind of hard to read because I'm not being super careful here. And then I could subtract 30 there. 18 minus 30 is negative 12 equals negative 30 e to the all that stuff is still the same. Negative 12 divided by negative 30 becomes positive 12/30 e equal to e to the all that stuff. 12/30 reduces to 2/5. So we got the natural log of 2/5 equal to the all that stuff, which I'm actually going to write this time. Natural log of 3/5 divided by 17t. And then you solve for t in the same way we solved for t in the previous problem. Where can I squeeze it? I'm going to squeeze it up here. Sorry, I know. It's only so much board space. Multiply by 17, divide by the natural log of 3/5 to get natural log of 2/5 times 17 over the natural log of 3/5. So that's the process for solving a problem like that. Okay. So I see some good questions. I'm trying to think about where I want to start. So let me leave that up while I think for a moment about where exactly I want to start. Sure. All right. So everyone's talking about anti-differentiation now. Let's do the other side here. We've got a few kind of typical rules, right? We know how to integrate powers of x or anti-differentiate powers of x. We know that the antiderivative of x to some power, like x to the 6th, is x to the 7th divided by 7 plus c. Or more generally, the integral of x to the nth power, or the antiderivative of x to the nth power, is x to the n plus 1 divided by n plus 1 plus a constant. And that's, of course, true, except for when n is equal to negative 1. Right? The integral, or antiderivative of x to the negative 1, is the integral of 1 over x, which I know we talked about last time. It's the natural log of the absolute value of x. Let's see. That's definitely one you're going to want to memorize, for sure. And then, let's see. Okay, oh yeah. And so, we also have the antiderivative of e to the x, z to the x. And then there's all the trig ones as well, which I'm not going to write down right this minute because I don't think that's what we're really focused on right now. But there definitely are trig functions we know the derivatives of, so we know the antiderivatives of those derivatives. But I think where you guys are going now is you're starting to talk about u-substitution. So I feel like Nicole threw out a good question there. The square root of 4x cubed times the square root of x to the 4th side. That's a great question. So let's go to the other side. So this question and a lot of these questions like this essentially revolve around the idea of undoing the chain rule. So just as a reminder, right, when you differentiate f of g of x, You take the derivative of the outside function, you leave the insides alone, you multiply by the derivative of the inside. All right, that's the chain rule. Now, yeah, definitely you, and don't worry, I've got you covered, Nicole. So the thing is, oftentimes people like to call g of x u. So we're going to say, oh, u is equal to g of x. And then if I take the derivative of both sides, well, there's lots of ways to write the derivative. If I write the derivative on the left, I can call it du dx. That's one way of writing the derivative. But I can also write it on the right-hand side as g prime of x. So now I'm going to replace, I'm going to rewrite this derivative. Now I'm going to use u's instead of g's. So I've got the derivative, and so I want to make a point before I say this. These were picked long ago. Someone decided that these were the right letters to use before maybe people started saying fu. So we've got the derivative of f of u equal to f prime of u times du dx. And so here's the thing. Oh, sorry, I don't want brackets around all that. I'm sorry. No brackets. So here's the thing. If I know that the derivative of f of u is equal to f prime of u times du dx, then I know that the antiderivative of f prime of u is equal to f of u. And that's kind of the idea that this u substitution idea revolves around. So let's actually look at the example that you put out there, Nicole, which is the antiderivative of 4x cubed times the square root of x to the fourth plus 5. Okay. So there's two things to think about when you're thinking about doing a u substitution. The first thing, well, Adam did it first. One of the things is that whatever you're choosing for your u, you are hoping, it's not always going to be true, but you're hoping that its derivative is also in your integrand. So with that in mind, and I want to use some different colors here. Sure, green. U equal to x to the fourth plus 5 is an excellent choice because the derivative du dx is equal to 4x cubed. So that is one thing to keep in mind when you're choosing what u might be, is that you hope that the derivative of u is also in your integral. The second thing we want to think about when picking u is if you don't have any kind of clear direction for what u might be, you want to pick something that is stuck inside another function. So I think of this x to the fourth plus 5 that is stuck inside the square root. Other examples of being stuck, which I will, yeah. So I'm going to erase, I don't want to erase that really, fine. Yeah. So other examples using the same choices of u and du would be something like this. The integral of 4x cubed times e to the x to the fourth plus 5. Or the integral of 4x cubed times cosine of x to the fourth plus 5. Or I'm going to do two more. The integral of 4x cubed divided by x to the fourth plus 5. Or the integral of 4x cubed times x to the fourth plus 5 to the fourth. All of these are examples of where you would choose u equal to x to the fourth plus 5 for two good reasons. The first reason being, yes, the derivative is also there, right? In each of these, the derivative of x to the fourth plus 5 is 4x cubed, which is showing up in all of these. And the second thing is that in each of these, the x to the fourth plus 5 is stuck. Here it's stuck inside the exponent. Here it's stuck inside the cosine function. Here it's stuck inside the denominator. If you wanted, you could also view this one as being equal to 4x cubed times x to the fourth plus 5 to the negative first power, which, oh yeah, that's definitely stuck. You can't do anything with that. This one also, you could multiply this one out right? X to the fourth plus 5 to the fourth power is not impossible to multiply out. But if it was to the, say, 41st power, then although not impossible to multiply out, it's certainly very, very challenging. So that's kind of the rationale for choosing u, is that you want to choose something whose derivative is there, and if you're not sure, you want to pick something that's kind of stuck inside the function. All right, so now, there's a couple ways people kind of deal with this. I personally prefer to do it this way. And I'll kind of show both ways. I like to then take this equation, du over dx equal to 4x cubed, and rewrite it as du equal to 4x cubed times dx. That's my preferred method because I see a 4x cubed times the dx. Oh, one more time, just in case you guys haven't gotten it. There's the link to the attendance. Please, please go fill out your attendance. So here's the thing. This 4x cubed times dx, that's equal to du. So when you're doing a u-substitution, you're actually translating your integral from having the variable x to having the variable u. And when you translate it, everything has to change. All the x's have to become u's. If there are any x's left, you can't do the integral yet, or the anti-differentiation yet. So the other thing to be aware of when you do this is you always want to make sure that you change the dx part to the du part before you do anything else. So if I'm going to rewrite my integral, it's going to end up equaling, so 4x cubed dx, that's going to be my du. And now that I've dealt with all of this stuff that's circled here, I'm left with what? What's the remaining part there? Square root of u. So we've changed our integral to being in terms of just u, and now we can anti-differentiate. I would probably rewrite this. I'd probably rewrite it as the integral of u to the 1/2 du, and then I would use the anti-power rule. So I'm going to add 1 to the power, divide by the new power, plus c. And then when you're done, after you've anti-differentiated it, if it's an indefinite integral or just an antiderivative, you should always be ending with the same variable that you started with. Since we started with an antiderivative of x, our answer should be a function of x. So we have to plug back in what x is equal to, so what u is equal to. So I'm going to rewrite this, instead of dividing by 3/2, I'm going to say this is equal to 2/3 times u to the 3/2, where u is x to the 4th plus 5. And that's how you answer that question. Now, the reason this works is exactly because of the chain rule. Let me show you. So if I look at this function here, the derivative of 2/3 times x to the 4th plus 5 to the 3/2 power plus c. Well, if I take the derivative of this, I have to use the chain rule. I'm going to get, so when you take the derivative of a constant times some stuff, I get a constant times the derivative of stuff. Well, the derivative something to the 3/2 power is going to be, the power comes down, I get 3/2 times my stuff to the 3/2 minus 1 is 1/2 power times the derivative of the insides here, just 4x cubed, plus the derivative of a constant, just 0. Well, look, this is exactly what I've got up here. These cancel out, and I get exactly this, which is the square root of x to the 4th plus 5 times 4x cubed. So that's how u-substitution works in general. Is you're picking u, you're finding du, dx, and you're hoping that it's showing up in your integral. And then you're replacing all the x things with the u things. After you've done that, then you can anti-differentiate, because this is something that's easy to anti-differentiate. It's just some function of u that's simple. And then we anti-differentiate, and we plug back in what x is. Or sorry, what u is. No, definitely. We're going to do lots of examples for sure. Are there any other questions about this one before I move on to another example?
So is your u always going to be like the second term?
I wouldn't say the second term, because I could have totally written this in the opposite order, right? I could have written this integral just as easily as the square root of x to the fourth plus 5 times 4x cubed dx. I would say that u is generally, okay, I'll just in a second, u is generally the thing that is stuck inside another function. That's my usual thought process.
Okay. So like with an exponent or like the square root like that.
Yeah, inside a root, inside an exponent, inside a trig function, inside a denominator. Those are all examples of being stuck. So I see someone else asked, I'm confused where the du went. So where the du went. So here's what happened. I said, so and there's actually two different ways of doing this. I'm going to show you guys, just to make sure everyone's super clear, I'm going to show you kind of the other imagining of this. This is we'll like do this slightly differently. It's still the same work. It just looks a little bit different. So my preferred way of doing this, just because that's how I learned it, is to say, oh, I have du dx equal to 4x cubed, and then I can bring this dx over here and say du is equal to 4x cubed times dx, and I exactly have a 4x cubed times dx. So that 4x cubed times dx got replaced, right? I just substituted. In fact, some people even rewrite it. I could rewrite this as the square root of x to the fourth plus 5 times 4x cubed dx, and say, oh, look, that is my du. And that is my u. So I'm replacing those things and getting exactly this. The integral of the square root of u du. Other people prefer to do something slightly different, which sometimes is fine. Sometimes I feel like works out less nicely, but I think it's just my own personal bias, to be honest. Some people don't do this part and they say, well, okay, du dx is 4x cubed. So what they then do is they say, okay, my integral of 4x cubed times the square root of x to the fourth plus 5 dx, they actually just take this and replace it with du dx. And they replace this with u. So then my integral becomes the integral of du dx times u, sorry, the square root of u times dx. But then the dx's cancel, and we've got the integral of the square root of u du, just like we have over here. If you do it this other way, you'll end up back in the same place. It's just a different way of getting there. So Moniz, hopefully that kind of answers your question about, yeah, okay, good, go. All right, so let's do more examples. And I definitely saw there was another question in the chat, so let me make sure I see what it is here. Sorry. Do you have to plus c for e to the x? Yeah, for sure. So if you're doing an indefinite integral, so actually, yeah. So just real quick, the antiderivative of e to the x is definitely e to the x plus c. If I wanted to find the area under the curve of e to the x between 0 and 1, which would look like this, if I'm finding this area here, then I don't need the plus c, right? If it's indefinite, you need the plus c. If it's definite, you don't need the plus c. But you do have to evaluate it. That means I'm gonna get e to the 1 minus e to the 0, which is e minus 1. And I would leave my answer like that, but some people might want to approximate it and say it's approximately 2.7 minus 1, 1.7. So yeah, generally, if you're doing an antiderivative, you need the plus c. My voice is getting tired. I can feel it. It's too much talking. Okay, let me take a sip of water here. So let's see, there was another, I thought there was another question here. I'm looking for just one sec. Can I make this longer? Yeah, I can, okay. Oh, there we go, cool. So here is a question. The integral of e to the x over, I'm gonna change it slightly just to be fun. It's not really gonna be that big a difference. Let's make it 5 plus e to the x. Okay, so what's a good choice for you here? Let me ask you guys. Is a good choice for you the thing on top or the thing on the bottom?
On the bottom.
Because the thing on the bottom is stuck. Exactly. So I'm going to let u equal 5 plus e to the x. Now, this is also a good choice because the derivative of that is exactly e to the x. And I have an e to the x. Now, here's where we have to be extra super careful. You do not want to replace all of your e to the x's with du dx. Right? It would be wrong, don't write this down, it would be wrong to say this. I mean, not wrong, but it wouldn't be helpful. That's going to screw us up big time. This is kind of why I like doing it the way I like to do it. So I really think it's helpful to say, okay, du is e to the x dx. And my first job after I've chosen my u, my first job is to make sure that I change whatever has a dx to something with a du. So making sure dx becomes du is the most important part of getting the u substitution done. So what I'm seeing is, oh, well, du is equal to e to the x times dx. So I'm going to say, there's my e to the x times dx. There's actually one other way of doing this, which I will also point out after I do this one. But I think this way works the nicest. So I'm going to start by rewriting my integral as well. E to the x times dx is du. Now, I like to write it, actually, I don't really care. You can write it on top of your fraction like that, du over whatever. So we'll do it this way and then we'll modify it. Now that I've dealt with dx becoming du, or something with dx becoming du, what should my denominator be? You guys can type it or say it. Awesome, yeah. U. Great, we've changed all of the x's to u's. We are now able to proceed with our anti-differentiation. Now here's the thing, some people struggle with writing it this way. It might be helpful, you don't have to. You'll probably get used to seeing this and being able to deal with it. But you might prefer to write this as 1 over u times du. That might make it easier to see what's going on there. What's the integral of 1 over u? The natural log of the absolute value of u. And then after we anti-differentiate, then we have to plug back in what u was equal to. So here we get the natural log of 5 plus e to the x plus c. I should say the natural log of the absolute value of 5 plus e to the x plus c. Now, one extra tiny little piece that is not super duper important is that some people, you might see them drop the absolute values in this particular problem. The reason why they drop the absolute values is because you don't need them here because 5 plus e to the x is already always positive. And if something's always positive, you don't need to say you're taking the absolute value. So some people might end up writing, this is just the natural log of 5 plus e to the x in parentheses plus c. But if you're not sure or don't want to worry about it, just always leave the absolute values and you'll always be safe. One other way people sometimes do this, which I want to point out. Again, this is not my preferred way of doing it, but some people do like to do it this way. So some people, same choice of u. Du dx is still e to the x. But then some people like to solve for dx, meaning they write this as du equal to e to the x times dx. and then they divide by e to the x. And then they just replace dx with this. And they start there. So they say, okay, this integral is going to be the integral of, you leave everything else alone for a minute, and you replace the dx with du over e to the x. And then look, usually what should happen, I just dropped my pen, sorry. Usually what should happen is that the thing that's below the du should cancel out. And it does. And then after that, you can replace the remaining things with x's. Well, 5 plus e to the x is exactly what we chose for u. So this becomes the integral of du over u, just like we had over here. So that's another way of doing the u substitution. Definitely. So we've seen a couple times that when you integrate 1 over x, the integral of 1 over x is the natural log of the absolute value of x. I'm just using a different variable here. So whenever you have the integral of 1 over something, I should say, when you have the integral of 1 over your variable, right, whether it's u or x or t, right, the integral of 1 over t dt is the natural log of the absolute value of t plus c. And the reason why is because the derivative of the natural log of the absolute value of x is 1 over x. And the derivative of the natural log of the absolute value of t is 1 over t. And I might make, so I don't want to explain that fully again in case there's more questions about that, because we did talk about it, I think, last time, but maybe I'll make, if my voice survives, maybe I'll make a short video later today explaining again why the integral of 1 over x has to be the natural log of the absolute value of x, so that you guys can look that on your own if you want to. It's a domain issue. All right, eraser. So I think I've answered all the questions you got. I have more u-substitution examples, but I just want to circle back around to, I know antiderivatives of exponential functions. Sure. And then, so Fernanda, I'm not exactly sure what you mean by finding indefinite integrals using the log rules. If you wanted to kind of clarify that, I would appreciate it. Otherwise, I don't know if I can answer your question because I'm not sure if I understand it exactly. And you're welcome to send it to me in a private chat if you want, or you're welcome to send it to me or say words or whatever. Let's see here. Oh, okay, that's how the form, oh, okay. Okay, well, that's fair. That seems like a weird phrasing for the homework, yeah. Okay. So something to be aware of, just very, very generally, I guess you could call it a log rule for indefinite integrals, although I think that's kind of weird language, is that if you're ever integrating some, and there's a number of ways you can write this. Sorry, I think of it this way. If you're integrating the derivative of a function over a function, you're always going to end up getting, I'm going to use g instead. Sorry, let me change that to g real quick, just because it seems a little more sensible. This is always going to end up being the natural log of the function in the denominator in absolute value. And here's the reason why. You can always do a u substitution here. U is going to be g of x, du dx. Well, the derivative of this is the derivative of that. That's just g prime of x. So I can rewrite my integral here. Well, g prime. So again, I wouldn't replace g prime with du dx. I would do this first. I would say that du equals g prime of x times dx. That is just my preferred way of doing it. Yeah. So then that's going to be du. The denominator is just u. So look, we're back where we were with the previous problem. This just becomes the integral of du over u, or 1 over u du. And we know how to do that. That's just that. which is just and here's how we know it's true. The derivative of the natural log of some stuff, right? If I do the derivative of the natural log of the absolute value of g of x, I would say if you ever have to differentiate this, just kind of ignore the absolute value. You're going to get 1 over the stuff times the derivative of the stuff, which is exactly the function we're starting with inside there. No plus c, that's crazy. I'm sorry, that's insane. Sorry. The derivative of the constant should be 0. Yeah, we can definitely do a, okay. So, let's see, what time is it? Okay, we can definitely get to a quotient. I want to do a few more. So when you say quotient, Abigail, I'm assuming you mean something like a bunch of, something like the second question I asked, or question 1b from the quiz, where it was a bunch of powers of x divided by another power of x. Is that what you mean? Cool. Yeah, we can do a quick one like that, and then I'm going to come back to more u-sub problems, because u-sub, so here's what I'm going to say about u-sub very generally. U-sub is probably the most prolific method of integration you will use. It comes up all the time, and eventually it's going to be the method you're going to be kind of happiest to see, because it's usually fairly straightforward. Not always, sometimes it's weird, but most of the time it's like, okay, this isn't so bad. But let's do a quotient one real quick. So the things, oh man. So the things about quotients are, if you've got something, let me think here for 1 sec. Yeah, we'll do 2 different quotients actually. One of them will be one way. Okay, sure. Okay. What have I got here? Sorry, brain. Come up with something. Sure. X to the 7th minus x to the 4th plus the cube root of x minus x to the negative 2nd, just to be stupid, over x to the 5th. So if you see a question like this, again, here's one more time. There's the attendance form. Oh, sorry, I just said that to not everybody. Apologies. When you send me a private message, then it makes me respond to you privately unless I change it. But now I don't know how to fix it. Everyone. And that's okay. You should definitely feel free. I'm doing something stupid here. I see. There we go. I should know how to fix that more easily. Please feel free to send me private messages. Not a problem. I just need to be slightly smarter than I am sometimes. So when you see an integral of a quotient like this, the clue here about what we need to do is that we have a fraction or a quotient where the denominator has 1 term in it, some power of x, and everything on top is powers of x. So when you have something like this, the idea is that you're supposed to divide each of the terms in the numerator by the denominator. And you can either, there's 2 different ways to imagine it. You can either do it as division, which is what I like. So x to the 7th divided by x to the 5th minus x to the 4th divided by x to the 5th plus the cube root of x, which we should definitely write as x to the 1/3 divided by x to the 5th minus x to the minus 2nd divided by x to the 5th dx. But you can also write it as all of this stuff on top times this brought up to the numerator as x to the negative 5th. Now do be careful. I saw a couple of you make this mistake on the quiz. When you have this, you have to multiply this term by everything in here. For some reason, sometimes people make the mistake of just saying it's all of this, like plus this or minus that for some reason. So be careful, don't make that error. In either case, here's what this integrand simplifies to. So you can do it this way, you're subtracting the powers, you get x squared. Or you can do it this way, x to the 7th times x to the negative 5th, you add the powers and you get x squared. Here, so although you can write this one as x to the minus 1, for some reason for me it's just better if I know I'm going to get x to the minus 1, I'd rather write it as 1 over x, because that is a clue to myself that, oh, I know the integral is going to be the natural log of the absolute value of x. So, and then here the subtraction is going to be weird. 1/3 minus 5. I might need to write that as 1/3 minus 5 times 3 over 1 times 3. So 1/3 minus 15/3 is negative 14/3. And it is usually preferred to use an improper fraction like this. You shouldn't use a mixed fraction or a decimal usually. Like somebody did to the negative 2.5 on the quiz, which is fine. But usually people write these as fractions. And then minus 2 minus 5 is minus 7, so it's minus x to the minus 7. And now that we've written everything as powers of x, we can use the anti-power rule, except for this one here. So we're going to get x cubed over 3, right? Because you add 1 divided by the power. The integral of 1 over x is the natural log of the absolute value of x. The integral of x to the negative 14/3 is x to the, so negative 14/3 plus 1 is negative 14/3 plus 3/3, which is negative 11/3, divided by the new power. And then minus negative 7 plus 1 is negative 6. Be careful, sometimes people make the mistake and say it's negative 8. All right, if you're adding 1 to a negative number, it becomes less negative. So the negative 6 divided by negative 6 plus c. And although you could leave your answer like this, I would simplify it a little bit and say it's equal to x to the 3rd over 3 plus the natural log of the absolute value of x. I would simplify this. I would flip and multiply and say minus 3/11 times x to the negative 11/3. And I would say minus and minus is plus x to the negative 6 over 6 plus c. That's how I would simplify that. So I think I just figured something out. I think if I don't talk so loud, it doesn't hurt my voice so much. But if I'm talking too quietly, please let me know. But I think that should be fine. So yeah, I'm going to do another quotient problem, but it's going to be very different.
If there's a constant in each of the x terms, would that make a difference in how you go about solving?
By constant, you mean like if I had, say, like 6 here?
Yeah, and in the denominator as well.
Like a 8 there?
Yeah.
Sure. So then for each of the terms of the denominator, so I'm going to put these in red here just to kind of show you the difference. So if I had, say, a 6 here and an 8 here, right, all those would get an 8. Here, the 6 would be there. And here it would be, so the 8 wouldn't come up. It would still be over 8. In fact, one thing you could do if you had the 8 in the denominator is you could actually pull it out in front and say it's just a 1/8 out in front of the integral. So you could put them in each of the terms, but you could say this 8 here is going to come out over here. That's often what people do when the entire thing is multiplied or divided by a constant. So we could have a 1/8 out here. We would have a 6 right there. And then we'd have a 1/8 and a 6. The plus c comes after that. You don't throw it on plus c. So yeah, so when you have a constant that you're multiplying or dividing by, it just kind of hangs out is what I usually say. Okay. Yeah, okay. So, let's look at this example. I think for 1 second here. Yeah, I want that to work out that way. So I would really like this to be something like 2x to the 4th plus 6x cubed plus 3x squared. And then, sorry, 1 second while I think. Okay. Here's another quotient. Clearly, this quotient does not fit the same criteria that the previous one did. Right? The previous quotient was a bunch of stuff divided by one term. And so that was fine. You could divide each thing by that one term. This quotient is not, right? It's a bunch of stuff divided by a bunch of stuff. So when you see a quotient like this, a rational function like this, right, where it's a polynomial, there's a lot of methods that are possible, which we haven't learned yet. But the first thing, when I see something complicated, and I'm talking about methods of integration, the first method I try to use is u-substitution. So, yeah, I'll say that later. So typically, I'm trying to pick u to be something whose derivative is also there. So it looks like, well, this is a 4th degree polynomial. This is a 3rd degree polynomial. The derivative of something to the 4th is something to the 3rd. So it might seem sensible to make this my choice for you. It might not work, right? Sometimes we choose the wrong thing and we have to start over. So I'm going to pick this. And then I'm going to find du dx. So the derivative here is 8x cubed plus 18x squared plus 6x. All right. Do I have that? Well, the answer is kind of. I don't exactly have that. But here's the thing. This thing here is actually a multiple of this thing here. So check this out. I can say that du equals, if I factor out a 2 from here, I'm left with exactly 4x cubed plus 9x squared plus 3x. So what I could do is then I could divide both sides by 2 and say du divided by 2, or often people write it as 1/2 du. 1/2 du equals this times dx. But look, this is exactly my 1/2 du. So how would I know if I chose the wrong thing? That's a good question. I'm trying to think about a good answer. I don't have a good answer at the moment, but I will circle back around to that, maybe not today. The kind of very basic answer to that question is, the way you know that you chose the wrong u is if the derivative isn't showing up, or if a multiple of the derivative isn't showing up. And here a multiple of the derivative is showing up, right? 2 times my derivative exactly showed up. So this is going to be the integral of 1/2 du divided by u. And now here's a couple things we usually do with this. This constant multiple, just like in this previous problem, this dividing by 8 we pulled out in front. This multiplying by 1/2 we're going to pull out in front. And then I like to write this as 1 over u du. So then I end up with 1/2. Integral of 1 over u for the 4th time is the natural log of the absolute value of u. And then we have a plus c, of course. And then at the end, we plug back in our choice for u. So I get 1/2 times the natural log of the absolute value of 2x to the 4th plus 6x cubed plus 3x squared plus 7. So that's how I do that problem. Okay, so more u-substitution examples. I'm trying to think if there's anything else on my list here that was super important. No, I think it was really just all u-sub. Yeah. Sure. I'll erase the other side of the board while back. Oh, I see someone just typed the question. 1 second. Okay, so let's see what's your question here. And the quotient is the denominator, normally the u. A lot of the time, not always. Well, so the thing is, it's usually not the numerator, but, well, actually, here's a good example. Let me think for 1 second here. That's a fine example. No, that's kind of garbage. No, okay, here's a good example. So we got e to the square root of x divided by the square root of x. And I am going to pick u equal to the square root of x because, yeah, it's stuck, right? Square root of x is stuck in the exponent and the denominator. But something, I don't say, it's not something weird's going to happen, it's just that you have to be careful when you rewrite things. Yeah, we can look at that one. That one, that's a tricky one, but yes. And then, yeah, okay. There's something I want to make sure I cover in the last couple minutes. So here I would definitely have u equal to the square root of x, or I would probably actually say u equal to x to the 1/2. And my du is equal to 1/2 x to the negative 1/2 dx. I usually get in the habit, instead of writing du dx equal to the derivative, I kind of automatically say du equal to the derivative times dx. Right? You could definitely, you could start with this, but then I immediately like to bring that over and say, oh yeah, because that's the way I like to do it. If you do it slightly differently, that's perfectly fine. Now, here is where you might get caught up if you're not being careful, if you're not making sure you change dx to du first. If I said, oh, here's u, I might write this as the integral of e to the u over u times dx. And then I'd have to do something weird, like go back and solve for dx. I don't want to do that. So here's the thing. Actually, I'm gonna leave that up just because. And this isn't really what I want. Although you could probably make that work if you really tried. I got a late joiner there. Here's the attendance form one more time. So what I would actually do here is say, okay, well, this du, I'm going to rewrite this just a little bit. This is 1/2. X to the negative 1/2 is 1 over x to the 1/2, or 1 over the square root of x dx. Now, if you look at this integral here, I have a dx over the square root of x right there. So I could say, well, look, 2 times du is equal to 1 over the square root of x dx. So I could rewrite this integral as e to the square root of x times 1 over square root of x dx, right? I could write it like this again, but I'm trying to make it really, really obvious that, oh, look, this part here, that's my 2 du. And now that I've dealt with changing this stuff into du, the rest of the things that haven't been dealt with, that gets to become a u right there. So this ends up being the integral of e to the u times 2 du. And again, I would automatically bring that constant multiple out in front. The integral of e to the u is e to the u. And then I replace u with what I chose. So you get 2 times e to the square root of x. And that's how you would do a problem like that. So what I'm trying to emphasize here is that just because you choose something for u, it doesn't mean that everything that looks like that should get replaced with u automatically. You have to deal with making sure dx changes to du before you can deal with replacing all the other things. Let's see. I'm going to answer Martha's question, and then I'm going to do something called what I like to call mini u-substitution. So this question here, which I'm going to change up just slightly to make it slightly different, just make you guys have to, I'm going to make it 6 over 1 plus e to the negative 6x. And this problem is what I would call a trick. And not so much as a trick is that you have to know the trick to do the problem. So when you see something with an e to the negative 6x in the bottom, like I would want to choose this to be my u, but the derivative isn't there, right? If I take u equal to 1 plus e to the negative 6x, my du is negative 6 times e to the negative 6x dx. So this is actually a good example of knowing that I didn't choose the right thing for you. Not because we chose something bad, but because, well, look, that I don't have that, right? I don't have e to the negative 6x times dx. But that actually gives me a clue in that I would like to kind of have something like e to the negative 6x times dx. I actually want to have e to the positive 6x times dx. So when you see something like this, there is kind of a trick, and it really just, you wouldn't know to do it unless you had already done it once before. So here you are. We're going to see how you do something like this. So the thing you're going to do is you're going to multiply by essentially e to the opposite power of this. So if this is e to the negative 6x, I'm going to multiply by e to the 6x over e to the 6x. If this was e to the positive 6x, I would multiply by e to the negative 6x over e to the negative 6x, whatever the opposite sign is. Okay, and then we're going to distribute. So I'm going to get 6 times e to the 6x. I don't want that 6 there really. Sorry. The 6 is there to make it easier. We don't really need it. I want to make it a little bit harder because it's not always going to be so nice. Let's just make that a 1. Now when I distribute this here, e to the 6x times 1 is e to the 6x. And e to the negative 6x times e to the 6x, well, when you multiply this together, you add the powers, and negative 6x plus 6x is 0. So you get e to the 0, but e to the 0 is just 1. But now we're in a great place to choose a good choice for u. So instead of this, now we're going to choose u equal to e to the 6x plus 1. By the way, just in general, if you ever have the ability, most of the time, if you ever have the choice between picking u equal to something or u equal to something plus a constant, you always want to include the plus the constant part because the derivative of that's just going to be 0. So it's going to make things usually nicer if you pick the plus 1 or the plus 5 or the minus 7 in there. My du here, the derivative of e to the 6x is e to the 6x times the derivative of 6x, which is 6. Now, I don't exactly have, so here's what I would say about this. If you ask me, do I have this in my integrand? I would say yes, essentially, because we can always fix a constant multiple problem by dividing them out. So I don't have 6 e to the 6x dx, I just have e to the 6x dx. Well, that's a problem that is easily compensated for. I can divide both sides by 6. 1/6 du equals e to the 6x dx. And then e to the 6x times dx gets replaced with 1/6 du. So here's what I've got. I've got the integral of, so here's the thing. I'm going to say 1/6 du, but I'm going to put the 1/6 multiplying outside because that's just what we do. Because you can always bring out constant multiples. Not constant adds or subtracts, but constant multiples or divisions. What do I have on the bottom here? Everybody.
You.
Uh-huh. Sorry, I'm looking like a spouse trying to drink on the straw. Yeah, exactly. And again, this comes a lot. The integral of du over u is the natural log of the absolute value of u. And then we replace u with what it's equal to. This is going to equal 1/6 the natural log of the absolute value of u. Let's see. And that would be my answer. And again, you might see someone drop the absolute values there because the insides are always positive. But again, not necessary. Okay, last thing I kind of want to cover here. Well, first thing I want to say is kind of along with that. Your du doesn't have to be exactly right. As long as you're good with the constant multiple, you're going to be fine. So for example, if I was integrating something like x to the 5th times e to the x to the 6th, I would say, oh, well, u is x to the 6th, because what's the derivative of x to the 6th? Well, what I'm actually saying in my brain is the derivative of x to the 6th is essentially x to the 5th. I know there's a multiple, but I really just care that I'm getting this about right. du dx is 6x to the 5th, but I just want those things. I want x to the 5th dx. So I fix it. I bring the dx over, I divide the 6. So that 1/6 du equals x to the 5th dx. So this here that I've just circled in green, that's going to be my 1/6 du. And then the rest of this that isn't circled, that's going to replace, so e to the x to the 6 is going to be e to the u. So e to the u times 1/6 du. I like to bring the 1/6 out in front, which I usually just do automatically when I'm writing the integral, is I bring the constant multiples out in front. And then finally, the integral of e to the u is e to the u plus c. We don't need to distribute the 1/6 to the c, because 1/6 times a constant is still just a constant. So whenever you're doing a multiple of an integral, you don't need to have that multiple extend to the constant there. We just write it as 1/6 e to the u plus c, and then replace the u with x to the 6th. So when you're looking for a choice of u, don't worry about being off by a constant multiple. That can always be adjusted for. Okay. I'm going to go a little bit over because there's like 2 examples I still want to do, because there's something I want you to get good at, which I think this might have been someone's question earlier on, but I kind of, I wouldn't say ignore, but just kind of got lost in all the stuff. So here's that attendance form one more time. If I want to do the integral of e to the 4x, you could totally do a u-substitution. But what I call this is a mini u-substitution, where the u-substitution is going to be such that the derivative is just a constant. If I make the choice of u equal to 4x, du is going to be 4 dx, or du dx is going to be 4. Du is 4 dx. 1/4 du equals dx. So here's what we end up seeing. Whenever you make a u-substitution where u is just a multiple of x, you always end up dividing your answer by that multiple. Right? So I know the integral of e to the x is e to the x. I know the integral of e to the 4 times x is e to the 4 times x divided by 4. So it's kind of like the opposite of the chain rule. If you were differentiating this, you would end up multiplying by 4. Since you're anti-differentiating, you're dividing by 4. And that's something that's always going to be true for choices of u that are just multiples of x. I can do it the long way and say, okay, well, this is going to be dx is 1/4 du, and e to the 4x is e to the u. The 1/4 comes out. Integral of e to the u is e to the u. And then u is equal to 4x. And that makes sense, because if I were to differentiate this, the derivative of e to the 4x would be e to the 4x times 4, which would cancel out with that 4 there. But this kind of, I think, is such a small u-substitution, my my goal for you all is to be able to do this without actually doing the u-substitution, at least when you're kind of working at your own head. So for example, what am I going to do? If I was going to do, say, the antiderivative of cosine of 7x. Okay, if I were going to take the derivative of cosine of 7x would be negative sine of 7x times 7, because I'm multiplying by the derivative of 7x. So the antiderivative is going to need to divide by 7 to compensate for the 7 we would multiply by when we were differentiating. So here's what I know. I know the antiderivative of cosine in general is positive sine. Antiderivative of cosine of x is sine of x. So the antiderivative of cosine of some stuff is sine of that stuff. This isn't exactly right yet. Why isn't this right? Well, because what's the derivative of sine of 7x? It's cosine of 7x times 7. But I don't have a times 7 here. So I need a 1/7 to compensate for the 7 I would multiply by when I differentiated. So this is actually the answer. The integral of cosine of 7x is sine of 7x divided by 7. And you could see this by doing the u-substitution. Right? You could have done u equal to 7x, du is 7 dx, and then rewrite this as du over 7 equals dx, so that this becomes the integral of cosine of u times dx, which is, oh look, there is where my division by 7 is coming from. And then we anti-differentiate that, we get positive sine of u divided by 7, and then finally replace u with 7x. So we'll talk more about this next time. But here's what I want you to take away from this. If you see that you are going to be making a u substitution where u is just a multiple of x, what's going to end up happening is it's going to work out kind of as normal, except you're going to end up dividing by whatever the coefficient of x is. All right, that is all I've got for today. I've got a couple of videos I know you guys want me to make, which I will try to do this afternoon. I'm going to try and talk quieter so that I can do more. And one last time, please do go fill out the attendance form once and only once. And a couple other things. If you have questions, start a discussion in Canvas. I will happily contribute to it. You can always shoot me an email, but I like it when you do discussions because then other people can see what you're asking about because they usually want to know too. So yeah, all right, that's all I got. I'm going to end it. Take care. I'll see you guys next week.